While neural networks and artificial intelligence and machine learning have been around since the dawn of AI research, it's only in the last decade or so that they have become the powerhouse machine learning technique. Using convolution and deep neural networks, these modern models can solve an almost endless series of tasks, including, it appears, full self-driving for Tesla and others. But how the heck do these things work? And what even are convolution and deep neural networks? Hey y'all, it's Dr. Know-It-All. In the first episode of this series, see the link above, and yes, it took me forever to get back to this topic, sorry. We discussed the history of neural networks and showed how a simple one works. Now it's time to turn up the heat and look at how real-world neural networks function and why they're so almost magically good at feature detection. As both deep neural networks and convolution are both really big topics, I'm dividing this up into two videos. Today we're going to discuss why convolution is necessary and what it is. In the next one, we'll discuss how they function in a deep neural network context. So here goes. Let's first examine why traditional neural networks are fine when small but become intractable when large. In this image, which shows about the simplest neural network that you can create, you can see we have 2 inputs, 3 nodes in the hidden layer, and 1 output node. Thus we have 6 nodes altogether. No big deal, right? But consider the connections between all these nodes. If we connect everything up, there are 6 connections between layer X and layer Y, and 3 from layer Y to layer Z. Plus there are 3 bias nodes in layer Y and 1 in layer Z. That's a total of 13 connections for 6 nodes. And again, if you're having problems with this, just go back and look at the former video where I talk about this in a lot more depth. And this connection number goes up really rapidly as you increase the number of nodes. If we just add a Y4 node to the hidden layer, the total connections goes up to 17, and it gets even worse if you add another hidden layer. For the same network, but with 2 hidden layers with 3 nodes each, a Y1 and Y2, you get 25 connections. That's 25 weights that can be altered by the neural network model, and that means 25 variables the program has to keep track of, and 25 partial derivatives that the program has to calculate to make changes. Well, this isn't so bad yet, right? 25 is pretty reasonable, so what's the big deal? Well, consider a very simple image, an MNIST digit that is 28 by 28 pixels. If you multiply that out, that's 784 input nodes. So now our X layer is 784 nodes. And if the next layer also has 784 nodes, 1 for each input, and there's only 1 output node, we get 617,009 node weights that we have to keep track of, and 617,009 partial derivatives we have to calculate and also keep track of. And that's for an absurdly tiny 28 by 28 pixel image that's barely even enough pixels to read a number from. A 1080p image, which is your basic high definition image that has 1 hidden layer of the same size and 1 output node, has around 4.3 trillion nodes and 4.3 trillion weights and 4.3 trillion partial derivatives to calculate. And that's only 1 hidden layer. Most deep neural networks have 12 or 15 or 20 or more hidden layers. Even with cutting edge mainframe computers, these numbers are simply too big. There's not enough memory or processing power to crank through all these calculations. And also, just as a historical fact, remember that fully digital neural networks have been around since at least the 1980s, and at that time processing power and memory was a tiny fraction of what it is today. So what's to be done about this problem? In a moment we're going to find out, but first, if you enjoy this video, definitely like it so other people can find it, because that's how YouTube works, and definitely subscribe so you can get the next episode in this series. I also want to make a really big shout out to my patrons on Patreon. You all are wonderful. Thank you so much for the support. We have 3 new members since last time: Stan Van Nice, Joan Gibbs, and Matt Miller. Thank you all so much. I really appreciate it. Also, a big thank you to Zenly Music for his intro and conclusion music. You can check him out on YouTube and Instagram. And don't forget, if you're in the market for a new Tesla, check out our referral link. If you use that and buy a car, we each get 1,000 free supercharger miles. And finally, don't forget that we are Amazon affiliates now. If you look below and click the link for your country, anything you buy from Amazon in the next couple of hours helps out our channel a little bit, so we really appreciate that. Thank you. So, how do AI researchers fix this literally huge problem? From the title of this video, I bet you can guess. It's convolution. But what the heck is convolution? Well, actually, convolution is something that you interact with every time you use an Instagram filter or many Photoshop filters and even some Snapchat filters. I, in fact, remember the first time I heard the term convolution was when I bought Kai's power tools back in the 1990s. And okay, oldsters, anybody else remember those amazing tools? If you do, definitely let me know in the comments, because it's pretty cool. One of the awesome tools that Kai designed was KPT Convolution. Convolver, a convolution-based filter explorer with a bizarre and really fun interface. Admittedly, at the time I bought this, I had no concept what convolve meant nor what a convolution filter was. But these filters turned out to be the key that unlocked deep neural networks by massively reducing the number of connections and thus weights and thus calculations and memory and processing between nodes in a deep neural network. So what is a convolution filter? Simple multiplication and addition, it turns out, just repeated over and over again. A convolution kernel is normally a square matrix with numbers in it. Let's look at two simple convolution kernels, a 3x3 Sobel edge detection kernel in the X or vertical and Y or horizontal direction. As a quick aside, the Sobel filter was invented, as you might imagine, by Erwin Sobel and Gary Feldman, so there you go. So what do we do with this filter? Well, what we do is we take an image, which is just numbers to a computer, and we lay one of these kernels over the image, then we move it across each pixel, multiplying the kernel value by the image pixel values, and then adding up each of the 9 multiplications together to sum up to one number. Yeah, this is a lot easier to explain if we look at a spreadsheet with a very small, quote, image. So as you can see here, the picture at the top is a 6x6 pixel image that has only one channel. In other words, it's a tiny 6x6 pixel grayscale image. Note that between columns C and D, there's a big jump in the numeric value, indicating the image goes from darker, which is around the 100 pixel values to the left, to brighter, which is around the 200 pixel values to the right. Let's explicitly multiply the top left corner, which is B2, 3, and 4, C2, 3, and 4, and D2, 3, and 4, by the vertical edge detection kernel. If we lay the 3x3 kernel over the 3x3 section of the picture, we get the following 9 values, 3 of which are of course 0, since 0 times anything is 0. Adding up these numbers, we get the 413 value that we can see in the result matrix. Next, we move the kernel over 1 pixel to the right, so starting with C2 in this case, and repeat the process over and over again until we get the entire result matrix. And also note that you go to the right, and then you skip down 1 row, and then you move back to the right, and then you skip down 1 row, and you move back to the right. So we're covering every single pixel in the whole image. And hey, let's look at this result matrix. What we get is really high values, or white, on the left, and really low values, or black, on the right. Yes, you'd have to normalize these values to fit within the 0 to 255 range expected in an image, but this kernel has nicely detected the image, as is quite obvious. There are, of course, many edge detection filters, and they can produce images like this one if run over a base picture. One other important thing to note here, the resulting image, or filtered image, is only 4x4, not 6x6 any longer. This is because the kernel is big. In other words, it can't go all the way up to the right or bottom edges, which causes it to lose a pixel in each direction, making it smaller than the original. In a very large image, this would be almost undetectable, but one can use what's called padding to resolve the issue. Basically, it just means you run the kernel over the edge by a pixel in this case, and thus you can retain the full resolution of the image at the next step if you wish to. Just to prove this vertical edge detection is not a fluke, let's run the horizontal edge detection filter over the same 6x6 pixel image. What do you get? A bunch of values very close to 0, showing that there is no edge detected there. These would show up as black in your output image, showing that there are no horizontal lines in the image. One last and super critical thing that we can do is use a stride bigger than 1. This is very critical to the way that convolution neural networks actually work, so let's examine what happens. So in this case, we're going to jump 2 steps over each time we run our kernel. So we start at B2 as the top left corner, and we run the kernel through that. But after we run that step, we don't go to C2, but to D2, skipping 1 cell. This is a stride of 2, and it happens vertically as well. We jump down from B2 to B4 rather than B3. So what do we get? With the bigger strides, we are down to a 2x2 matrix now, which is much smaller than our original 6x6 matrix. In fact, it's 1/9 the size. But check this out. This much reduced matrix still detects the edge that was in the original. And herein lies the magic of using convolution kernels with deep neural networks. You massively reduce the dimensions of the problem while extracting the useful information you need. Using a convolution kernel with a multi-step stride provides what's termed feature extraction. In other words, in this case, we extract the feature of the vertical line into a much smaller package, or more precisely, we reduce the dimensionality of the layer. In machine learning speak, the kernels are termed filters, as they filter out useful information like vertical lines. How do we specifically use these kernels in an actual neural network? What we don't do is predetermine their values. Above, someone named Sobel figured out that the 3x3 kernel numbers would do vertical edge detection, but we don't know ahead of time in a neural network what kernel values might be useful. So So we randomly select small values for the kernel, which become the equivalent of our node weights from before, and we train those weights through the network. So in the case of this 3x3 tic-tac-toe board, right, instead of -1, -2, -1, 0, 0, 0, 1, 2, 1, it might be 0.07, 0.5, -0.3, etc., right? Each one has some random value. And actually what those random values are that it initializes with are really important. There's some popular ones like Xavier and Atom that give a certain kind of range to those numbers and certain values, and it helps the network to do a better job of training. Anyway, what happens with these convolution layers is the network thus discovers the values, what values are correct to put into these kernels, which then determines what features they detect and extract. But you might say, wait, in order to extract a lot of features like vertical lines and horizontal lines, etc., we need a lot of kernels. So what we do is not just throw one randomly valued kernel at the image, but a whole bunch. Our first layer might perhaps create 64 randomly valued 3x3 kernels and run each of them over the input image. Each of those 64 kernels, or filters, can then learn to detect a different feature of the image. Perhaps one learns to detect vertical edges, another learns to detect horizontal edges, another 45-degree edges, another curves, another red to blue transitions, and so on and so on. Of course, we do not know ahead of time what these filters will learn, and that's part of the reason why convolutional neural networks seem, even to us researchers, somewhat magical. They figure out all sorts of features that we might not even recognize ourselves in an image or another data item. And one final important point here before we wrap up this episode. These kernels not only extract features, but make the entire neural model much smaller because they reduce the dimensions of the problem very rapidly. Let's think back to our 1080p image with 1920 by 1080 pixels with one hidden layer and a single output node. This is not a network that would do much of anything, by the by, it's just an example. With a fully connected traditional neural network, there are about 4.3 trillion weights the model has to store and adjust. If we use a 5x5 kernel and a stride of 5, in other words, we skip over 5 pixels each time at each step, we reduce the second layer's dimensions from more than 2 million down to 82,944. Now, we have to multiply this by 25, because the kernel is 5x5, and 64, which is the number of filters we're going to train on, so we end up with around 133 million weights in this network, which is still a lot, but this is about 10,000 times smaller than the 4.3 trillion number we had before. Suddenly, a previously impossible problem has become one that we can actually work on, at least with contemporary memory and processing power. So I'm guessing that's enough to make your head spin. It certainly does it for me too. So we're going to stop this episode here. Definitely subscribe, however, so you can catch the next one where we're going to put our convolution kernels into a deep neural network and see how the real magic happens. In the meantime, please feel free to ask me questions in the comments or at my email address, which is drknowitallknows@gmail.com. Till next time, bye-bye.